So let's look at this problem first. PV diagram problem number 1, a fairly simple process. 2 moles of a monatomic ideal gas go through this thermodynamic process from point A to point B. The pressure, 5 times 10 to the 5th pascals at P1. And the temperature at position A, at state A, 400 degrees Celsius. And we're going to fill in everything we can. We're going to figure out everything we can about this, both the states and the process going from A to B. So first of all, let's fill in what we know. The pressure at A, 5 times 10 to the 5th pascals. What units do we use when we use our ideal gas law? Let me write it down here. We use pascals, meters cubed, moles, Kelvin, and R 8.31. And the units work out nicely with this. Okay, so the units for pressure are correct. We'll put that in here, 5 times 10 to the 5th pascals. And at point B, it's the same. This is a constant pressure process. So that information is given. And the temperature at A is given. So I can enter it in. There's one problem, though. It's not given in Kelvin. So I need to add 273 to that. And that's what I'm going to use here, 673 Kelvin. Now we want to start, that's all that's given, right? That's everything that's given. We don't know V1. We know that V2 here, or the volume at B, is twice the volume at A. That's given. But we don't know what those are. So the first thing we see, PV equals nRT. We know everything. We can figure out what the volume is at state A. So let's do that first. So I could put A subscripts on everything. The number of moles is not changing because our piston doesn't leak. So the number of moles is a constant, and that was given in the problem, 2 moles. So we're trying to find the volume at A, and that's going to equal nRT over the pressure, 8.31, 673 Kelvin, and the pressure was 5 times 10 to the 5th pascals. And I end up with 2.24 times 10 to the minus 2 meters cubed. So I'm going to go ahead and enter that into my table. Oops, that's a negative 2. There we go. So I could solve for that right off. The next thing I'm going to do is look at my PV diagram, and I see that the volume at B is twice the volume at A. That was given down here on the axis. So I can then fill in my volume for B. 4.48 times 10 to the minus 2 cubic meters. If I know my pressure and my volume, I can use PV equals nRT to solve for the temperature. Remember, pressure in pascals, volume in cubic meters, 2 moles, 8.31 for our gas constant. I got 1,346 Kelvin, so I can put that in over here. And now I'm interested in the process going from A to B. So the first thing I see is change in internal energy, delta U. Well, if we're talking about a monatomic ideal gas, the internal energy is proportional to the temperature. I know the temperature at state A. I know the temperature at state B. You may have noticed I added a line here for internal energy. So this is why I do this. Once I know the temperatures, I can determine the internal energy at those two states. And then I can find the change as I go from one to the other. So let me do that. So I'm finding U, and this only works for a monatomic ideal gas. Three halves NKT or 3/2 nRT. So I'll use the second one I have here. 3/2, 2 moles, 8.31 joules per mole Kelvin, and 673 Kelvin is the temperature at state A. 16,778 joules. And you can do the same thing It's just proportional to the temperature. Twice as much in this case. This is in energy, it's in joules. Okay, so I'll enter those into my table. 16,778 and 33,556 joules are my two. So now I can find delta U. Delta is always final minus initial. In this case, it's B minus A. So I end up with a positive 16,778 joules. If I was going the opposite direction, if I was going from B to A, then I'd get a negative delta U. You have to be careful with your signs. So this is a positive. I'm going to put it in here just to make sure I've got it. I'm driving home the point that you have to be careful of your signs. I'm going to put a plus sign here. This is a positive 16,778 joules for my change in energy. It increases. The internal energy of my system increased. Okay, we've got two things left. Q, how much heat went into or came out of the system, and work done. So which one are we going to hit? Well, let's take a look at our graph. We know something about these graphs. The area under the curve on a PV diagram is equal to the work done. And that's the area under the curve. and that's the work done by the system. So if the gas expands, if the volume increases, which it did, we went from left to right, the volume increased, then we do positive work. The system is doing positive work. It's expanding. It's pushing the cylinder up, the piston up, and our force is up, so we get positive work. If it's going the other direction, if the volume is getting smaller, if the gas is being compressed, then the system is doing negative work. So in this case, the work done is positive, and it's the area under the curve. And because P is constant, this is very easy to find. It's just P times delta V. It's a rectangle. It's the height times the width. So that's an easy one to find. So we're going to do that. We know the V's, we know P, so we can find the work done. So that's our pressure. Our delta V was 2V1 minus V1, which is just V1. And I told you it's positive in this case because the volume is expanding. So I'm driving home the point that you need to be careful with signs. Positive, 11,200 joules. Let me put that into my table. So I've got one thing left, Q. And how do I get that? I use my first law of thermodynamics. I know that delta U is Q minus the work done by the system. And what do I end up with here? So that means that Q is equal to delta U plus W. And that was 16,778 plus 11,200. Again, it was positive 27,978 joules. So let's think about that for a second. Let's see if those numbers make sense. Maybe we forgot a minus sign somewhere. We want to make sure that everything makes sense. Our gas expanded from A to B at constant pressure. So if gas expands, usually if our container were to double in size, we might expect the pressure to come down. We might expect that, right? As the container gets bigger, the molecules have longer to travel in the container. They don't get to strike the walls as frequently. Your pressure is going to go down. But our pressure stayed the same. So how could it have stayed the same? Well, we put some heat in. We heated up the gas molecules so that they were moving faster. So even though the volume is bigger, they still collided with the wall enough to keep the pressure the same. So they had to be moving faster because they're covering a bigger area now. So we had to have put heat in. We know that W has to be positive because our volume is increasing. And we know that we had to put heat in. And if both of these are positive, well, if this is bigger than that, then we end up increasing our delta U. If this is smaller than that, then delta U would have gone down. So looking at the numbers here, the plus signs on Q and W make sense. And since Q is larger, a positive delta U makes sense. Okay, we started with a nice simple process. Let's look at one that's a little more interesting.